Okay, so if you would take a look at the notes that I just handed out, a few starter questions. These are just reminders of some things that you would have learned in your 1010 class, maybe Algebra 2, of dealing with exponents. So if I have an exponential, so I've got b raised to the m, and then I've got b raised to the n. What do I do with the exponents when I'm multiplying? So for example, if I have x squared times x cubed, what do I do with the exponents? I add them. So this is going to be b to the m plus n. So in this case, I'm going to get x to the 2 plus 3, or we just write that x to the 5th, right? What if I have a power raised to a power? What do I do there? Okay, we multiply them. So that's going to be b to the m times n. So if I have x squared raised to the 3rd, that's going to be x to the 6th. Okay, and people get those confused all the time. There's a nice property of exponents that allows us to kind of distribute this in here. So we can apply the exponent to each one of these. So this is going to be a to the n times b to the n. So for instance, if we had 2x raised to the 3rd, that would be 2 to the 3rd and x to the 3rd. So the easiest way to write that would be 8x to the 3rd. And then a quick reminder, what does a negative in the exponent mean? Means reciprocal. So we're going to write this as 1 over b to the n. So if I have x to the negative 2, that's going to be 1 over x to the 2nd. It's a way of changing the sign of the exponent if we do the reciprocal. Okay? And then again, what is any number raised to the 0 power? That's a 1. Okay? And what is 1 raised to any number? That's also going to be 1. Okay? All right, so a quick reminder on those. Now, in the last section, we talked about inverses and one-to-one functions and all that sort of stuff. And we made a big deal of making a point as to why it has to be a one-to-one function. We like working with one-to-one functions. And Emily, what was that answer again? Why do we like it to be a one-to-one function? Because the inverse will also be a function, okay? If the original function is a one-to-one function, that means its inverse will also be a one-to-one function. Now, there are lots of different one-to-one functions that we're interested in. There's a couple in particular because we use them so often, and the one that we're going to talk about today is an exponential. You would have done this in 1010, so some of this is going to be a review, but we're going to add to that just a little bit. So an exponential function looks like this. It's a to the x. So you'll notice that the base is a positive number, okay, other than 1, and the exponent is a variable. Exponent is the variable. Okay, so we call this exponential base a. They all have names. If you refer to them the right way, it makes more sense in the long run. It also helps you understand what its inverse is. Okay? Just like any other function, an exponential function makes a shape when we graph it. So we're going to take a look at 3 different functions here. So the first one is 3x. The next one is x to the 3rd. And the next one is exponential base 3, or that would be 3 to the x. So you'll notice that all of them have an x, and all of them have a 3, but each time they're in a different place. That's enough to make a huge difference in the shape that it makes. Okay? Can somebody describe this shape right here?
Line.
It's a line. Okay, what does the 3 represent? Okay, somebody said it back here. It represents the slope. Okay, so we're talking about a line with a slope of 3. So it looks something like that. Okay, now if we make this into kind of this is called a power function. Okay, so if the base is a variable and the exponent is now a 3, then we get a power function. This is an odd power function, and it looks like this. This is one that we've graphed before. So it has this shape right here, starts down here and ends up there. So there's our power function. Now, an exponential is different. It's not this shape, and it's not this shape. Okay? Exponentials have a completely different shape, and that's what we're going to look at now. So let's figure out what this looks like, and let's do this by plotting points. You can always plot points to figure out what the new shape is. So I'm going to plug in, let's find the easiest one first. We're going to plug in a 0. So that would be 3 is the base. That doesn't change. And we're going to plug in a 0. What happens when I do 3 to the 0? What's my answer? Answer's 1. The next easiest one is when I plug in a 1. So I have 3 to the 1st power. What's 3 to the 1st power? 3. And when I plug in a negative 1, what does the negative mean? Reciprocal. So this is going to be 1 over 3 to the first, or that's going to be 1/3. Okay? So let's go ahead and graph these points here. So we're going to graph 0, 1, 1, 3, and then I'm going to graph -1 and 1/3, back 1 and up 1/3. You kind of have to eyeball this. Just get as close as you can. That looks like about 1/3 to me. So we've got these points right here. So it's definitely not a line. There's a curve to it. It looks something like this. And then we want to talk about what happens out on the ends here. So if I were to plug in a 2, this would be 3 squared, and 3 squared is 9. So what happens is this grows really quickly. I'd have to go way up here to get to the next point. So it gets really steep. So it continues in that direction. What if I plugged in a -2? That would be 1 over 3 squared. So that would be 1/9. So that would be back 2 and up 1/9. We're barely above the x-axis. And what happens here, keep in mind that this base is a positive number. So whenever I take a positive number and raise it to a power, I'm still going to have a positive. So this is never going to go below the x-axis. In fact, it's never even going to touch the x-axis because it's always positive. So this has what we call a horizontal asymptote out on this end. Does this ring a bell? You saw these in 1010? Okay. So the domain for this, you can plug in anything you want. You can plug in from -infinity to infinity. But what about the range? Okay, it's going to be 0 to infinity. We definitely don't get out any negatives. It's always going to be around infinity. What about the 0? Does it ever actually equal 0? Do we do a round or a square one there? We're going to do a round one there because it's never actually going to equal that. Okay? All right, any questions? Okay, so let's pick some x's and figure out the y's that go along with it. For this is exponential base 1/3. So now the base is this fraction. It's still a positive number, so that's good. We definitely need that. So we're going to plug in these three numbers, -1, 0, and 1. Again, the easiest one to plug in is a 0 because what's any number to the 0 power? That's going to be a 1. If I raise this to the first power, that's going to be, that's going to be a 1/3. Okay, now here's the interesting one. What if I put in a -1 right here? So if I do 1/3 to the -1, you get +3 because here's what happens. I can apply the exponent to the top and bottom. So the top is a 1, the bottom is a 3 to the -1. And then if I want to change the sign of the exponent, I move it from the bottom to the top. So this is 3 to the first power or just 3. Okay? Or the quick way to think of it is, what does the negative mean? Reciprocal. What's the reciprocal of 1/3? 3. So we're going to graph -1, 3, 0, 1, and 1, 1/3. So this is the same type of shape. It just looks like this. Instead of starting small and getting really big, instead of exponentially growing, this is what we call exponential decay. It starts big and gets really small. It still has a horizontal asymptote of y equals 0, just like that one has a horizontal asymptote of y equals 0. What's the domain? Plug in anything you want. Get out only positives. Okay, so from 0 to infinity. Okay, are there any questions there? All right, raise your hand if this rings a bell, makes sense, saw this in 1010, piece of cake. Good. Then you can fill in this box right here. Okay, this is what you were taught in 1010. All, pardon me, all exponential functions behave this way. So we've got to have a positive number for the base, and this is going to be the exponent. It always goes through these 3 points. These are important because on each one of these, notice this is where the bend happens. So we want to keep track of those 3 points. Those are the important ones on the parent graph. So it goes through -1, 1 over a. It always goes through 0, 1, and it goes through 1 comma whatever the base is. Again, the name of this function is exponential base a. When you see it, you want to see it that way. So the examples that we did here, exponential base 3, exponential base 1/3. Okay, that tells us like the category of the function. Okay, the base has to be a positive number other than 1. Okay? Exponential growth if the base is bigger than 1. So like we had up here, we had 3 to the x, exponential base 3, that was growth, and 1/3, that was decay. It's exponential decay if the base is between 0 and 1. So if you've got a fraction or a decimal between 0 and 1, it's going to start big and get small. It's going to decay or shrink in size. And for these parent functions, the domain is always negative infinity to infinity. All reals. You can plug anything you want into an exponential function. That's one nice thing about them. And the range is always going to be all positive numbers because we're taking a positive number and raising it to a power. We're always going to get a positive out. Okay? What's the horizontal asymptote on all these? Y equals 0. Okay? Y equals 0. Okay. Any questions? Okay, then let's take a quick look at this. What's the name of this function? Exponential base 4. What's the name of this one? Exponential base 1/2. Is this going to be growth or decay? Growth, because it's bigger than 1. Is this going to be growth or decay? Decay, because it's less than 1. Now, I'd like you to graph these without using an XY table. We only do this to get used to how these shapes work. Once you know what this box says right here, and once you've got that figured out, you should graph these points. So if it's going to be 4 to the x, you're going to graph the points like this. You're always going to do it in this order. Watch, please. Everybody watch. -1, 0, and 1. You can always fill in this one right here. What's this one always going to be regardless of what the base is? That's going to be a 1. This is going to be the reciprocal of the base, so that's going to be 1/4. And that's going to be the same as the base, that's going to be a 4. Okay? So really the only two parts you have to really be concerned with are those guys right there. So it's going to be -1, 1/4, 0, 1, and 1, 4. So there is our exponential growth. Here's our horizontal asymptote of y equals 0. Okay? So you'd want to label each one of those points. Okay, make sure those are clear. Again, that's 1, 4, 0, 1, and -1, 1/4. Okay? If you draw that graph and label the asymptote and label those points, everybody's going to know you know what you're doing. Okay? Any questions? Okay. Let's label the points on this one. I'm going to change colors here. We're going to label 3 points on the parent graph here. -1, 0, and 1, that's always a 1. So you can fill in 4 of those 6 pieces of information right away. This is always -1. It's going to be the reciprocal of the base. What's the reciprocal of 1/2? 2. So we put a 2 here. This is always going to be whatever the base is, so that's going to be a 1/2. And then we just draw and label those 3 points. So -1, 2. 0, 1, and this point right here would be 1, 1/2. So I've got those 3 points. I connect them so that it looks like exponential decay. It's decreasing in size. And I label the horizontal asymptote of y equals 0. It comes out here, it just continues to get closer and closer and closer to the x-axis, but never actually touches it. Okay, any questions there? Sure? Raise your hand if this is easy. Piece of cake? Excellent. Okay, flip the page over. Okay, quick reminder of how we transform functions, how we can take them, stretch them, shrink them, flip them, slide them right, left, up, down, all that sort of stuff. Okay, this hopefully is a fairly familiar shape. We should know what the parent graph of that is. We practiced that the other day. It's a square root graph. So could somebody describe that for us? Goes like this. Top half of a sideways parabola, right? Top half of a sideways parabola. We're going to take that top half of a sideways parabola and we're going to, what does the 2 do to it? Vertically stretches it, okay? Makes it taller, twice as tall. What does the -1 do? Okay, that's going to be right 1. And what does the -3 do? Down 3. So I'm going to take that normal shape that looks like this, and I'm going to move it right 1, down 3. So I'm going to go to the right 1 and down 3. Okay, that's the starting point. And then I normally go over 1 and up the square root of 1. So I normally go over 1 and up 1. I'm going to go over 1 and up 2. I normally go, what's the next most convenient point to graph here? Over 4 and up 2, right? I'm going to go over 4, so count over 1, 2, 3, 4. I normally go up 2, I'm going to go up twice as far, so I'm going to go up 4. So I'm going to go up 1, 2, 3, 4. So we're right here. Connect those points. Okay, does that look like the top half of a sideways parabola that's been moved to the right and down and then made taller? Looks right, doesn't it? Okay, we'd want to be able to label these points. So again, this point is 1, negative 3. What would that point be then? 2, negative 1, excellent. And this one right here, we went over 4 from here, so that's going to put us at 5. And we went up 4 from negative 3. So that's going to put us at 5, 1. Okay? All right. Are there any questions there? The other ones are a little easier. There's not quite as much going on. Okay. What does this do? Okay. This is a vertical flip. That means it's reflected across the y-axis. So instead of being the top half of a sideways parabola, what do we have now? Bottom half of a sideways parabola. Okay? Could you label 3 key points on that? Still 0, 0. Not 1, 1. Now it's 1, negative 1. And normally we go over 4 and up the square root of 4. We're going to go over 4 and down the square root of 4. So that's going to be 4, negative 2. Now, take a good look at this one. This next one is really important. You don't see these very often, and you didn't do very many of these in 1010, and we didn't do very many of these when we studied transformations in Chapter 3. Can somebody tell me, what does that negative in front do? Okay, same thing it just did with that previous one. That is a vertical flip. What does that negative inside with the x do? Doesn't make them imaginary. Turns it sideways, okay? If this is a vertical flip, remember anything that's done after the function makes the shape changes it in the vertical direction, we're changing the x by multiplying x by a negative first. So we're taking all the positives and making them negative, and all the negatives and making them positive, okay? So this is a horizontal flip. So we're going to take this graph here, that graph that we normally have, that parent graph, okay, that top half of a sideways parabola, and we're going to do 2 things with it. We're going to vertically flip it, so we're going to flop it down here, and then we're going to horizontally flip it. So we're going to change the right side for the left side, so that's going to be that shape right there. So this is the original. I'll erase that. This is the vertical flip. I'll erase that. The final answer is both a horizontal and a vertical flip of the original one. So that's still 0, 0. Where is that point and where is that point? And negative 4, negative 2. Excellent. Okay. Any questions? Okay. Can somebody tell me what's wrong with the way this one's written? Yeah.
4's out front.
4's out in front. We normally don't do that. Normally we'd write it this way. Negative square root x plus 2. That's a positive 4. Okay. What does that positive 4 do? Up 4. What does that positive 2 do? Left 2. And what does that negative do? That's going to be a vertical flip. Has it been stretched or shrunk? Nope. We just take the regular old shape and we're going to vertically flip it. So it's going to be down here. So that's the graph I'm working with now. There's the vertical flip. What do I need to do with that to put it in the right place? I need to go up 4, and I need to go left 2. So I'm going to take each one of these points, and I'm going to go 1, 2, 3, 4, left 2, 1, 2. Could you label that point? -2, 4. I need to take this point right here, and I need to go up 4, and I need to go left 2. So I'm going to go 1, 2, 3, 4, and left 2, 1, 2. I need to take this point right here, and I need to do the same thing with it. Let's make sure we've got this point figured out. If we were at 1, -1, and I went up 4, that would give me a y coordinate of 3, right? If I was at 1 and I went back 2, that would put me at an x coordinate of -1. Everybody good there? Okay, this point right here is 4, -2. Figure out where that ends up. We've got to go up 4 and back 2. Up 4 and left 2. If you go up 4, that puts you at 2. If you go back 2, that puts you at 2. So this is 2, 2. So I'm going to take a look at this graph right here. Here's what we've got. This is the right shape. And I'm going to come back here, and I'll do this in blue. Does this look like the original one has been vertically flipped? So it's the bottom half of a sideways parabola, and it's been moved up 4 and back 2? Yeah. Okay. All right. That's a good review. Please make sure you review those notes. Please make sure you have that stuff about parent functions of exponential graphs memorized, because we're going to take those, and tomorrow we're going to move them left, right, up, down, stretch them, shrink them, all that sort of stuff.